Okay, today's tutorial is going to be on Dirac notation and symbolic evaluation. And what we're going to show you here is that you don't have to know the mathematical form of a wave function to get an answer, and even better, to get a useful answer. So what we're going to do is over here in the left-hand column, we're going to have the Dirac notation, and we're going to translate that into the more familiar integral notation over on the right-hand side. Our problem that we want to solve here is to evaluate the root mean square, the RMS of the linear momentum. All right, I'm going to show you how to do that. And in order to do that, what we'll need to do is calculate, right? A lot of physical chemistry is translating words into algebra, and that's what we're going to do here, right? We need to calculate the expectation value of the square of the quantity, the linear momentum operator, minus the expectation value of the linear momentum. We're going to indicate operators with a little circumflex, right, with this hat. So P hat, that's the linear momentum operator. And expectation values, well, expectation values are numbers, and we're going to indicate those with these angle brackets, right? The expectation value of the linear momentum is indicated that way. Expectation value of P, P hat, the operator, this one is a number. So in order to solve this problem, we need to calculate the expectation value of this new operator, P hat minus the expectation value of P, and we got to take the square of that quantity. In Dirac notation, an expectation value is always given by a bracket of a wave function and its complex conjugate, that is psi, the ket of psi, and then we have our operator in the middle, and then we have the complex conjugate of psi, that's the bra of psi over here. So this bracket here of psi with our operator P hat minus the expectation value of P, the full quantity squared. Our operator in here is an algebraic expression, and just like any other algebraic expression, we can expand that term. And to expand the square of this quantity, we take the square of the first term, and then we're going to multiply the first times the second, then we'll multiply the second times the first, and then we'll take the square of the last term. The order of operation is important in quantum mechanics, so I'm explicitly going to write these two terms here. What we'll find is that if we're just multiplying by a constant, the order of operation won't be important, but in principle, the order of operation is important, and therefore, to emphasize that, I'll write those two as two separate terms for right now. Now we just have our four terms here. We're going to substitute them back into the bracket. So let's write that out, right? We have expanded this out, and then we've expanded our operator into an operator of four terms, the sum of four terms. And if we have an operator that is represented by the sum of terms, then concentrating just on this right-hand side here, right? A bracket that has an operator that is the sum of four terms can be expressed as the sum of four brackets. We just will take that first term here and use that as our operator in the first bracket. The second term, we'll put that in the middle there of our second bracket, the third and the fourth. And now we can evaluate each of these four terms independently and sum them all up to get our answer. That's our strategy here. So let's take a look at that first term. Our first term here is P hat squared, the operator squared. Remember, an operator squared, you just have to do the operation twice. Okay, so we've got a wave function, its complex conjugate, and then the operator in the middle. This bracket, that is, by definition, the expectation value of the operator squared. Okay, so we know that that's going to be the expectation value of P squared. Good. The second term, well, an expectation value like this one, right? An expectation value is a number, it's a constant, right? And a constant So a constant there, an expectation value of P, a constant can be pulled out of a bracket, just like a constant can be pulled out of an integral, right? Leaving an integral behind. So too, a constant can be pulled out of a bracket. And that'll give us the expectation value of P times this bracket here. The third term looks just the same. The third term, we had a different order, right? We had the expectation value of P times the operator P hat, but in this case, we don't have to worry about the order of operation, right? An expectation value, a number, can be pulled out of the bracket, leaving us with the expectation value of P times this bracket, psi operate or P hat operating on psi, and then multiplied by the complex conjugate, and we integrate over all of that. That's what that bracket gives us. All right. The square of a number is also a number, a constant, right? So similarly here, the expectation value of P squared is a number, and we can pull that out of the integral, giving us the expectation value of P squared times this bracket here. Let's put all those four terms together, right? And therefore, the four terms that we had, the four brackets that we had, are equal to the expectation value of P squared minus the expectation value of P times the bracket psi, P hat psi, minus the expectation value of P times that same bracket, and the square of the expectation value of P times the bracket of psi on psi. The second and third terms, right? Oh, wait a second. This bracket here is exactly the expectation value of P, right? An expectation value is an operator between the wave functions in our bracket, right? So we can evaluate those, and those two evaluate to exactly the same thing. So they equal minus 2p squared, the sum of the second and third terms with the proper signs there, right? Give us minus 2 times the square of the expectation value of P. This fourth term, oh, look at that bracket there. That bracket, the bracket of psi on psi, that's just the normalization condition. We have an orthonormal basis set, and therefore the bracket of psi on psi, that's just equal to 1, right? So this term will be equal to 1, and the fourth term altogether is equal to the square of the expectation value of P. We've evaluated each of the four terms now. So let's put them all together. We put them all together, put the left-hand side in here that we evaluated initially. The four terms that we got by expanding that operator are now equal to the expectation value of P squared minus, oh, these two terms, that's the expectation value of P squared. We can do the sum there and find that the operator that we started with and evaluation of that expectation value of that operator is equal to the expectation value of P squared minus the square of the expectation value. And that is exactly, as was to be shown, the RMS value of the linear momentum operator. So hopefully this example has helped you to see how we can use Dirac notation and the evaluation of these symbolic elements, right, without knowing the actual form of the wave function, right, and use things such as the definition of an expectation value and the orthonormality condition.